Yes. If there's no questions on the homework, what we're looking at today is actually with radicals. Now, I put this first one on here. We don't have it on there, but I feel like for the most part, we felt comfortable with what we did yesterday, 521, properties of exponentials or exponents, or properties of exponents. Simplest form. So, simplest form with radicals, it has to follow these main three things. One, no radicals can have perfect nth powers as factors other than 1. What that's saying is, in simplest terms, I can't leave the square root of 8. I cannot leave a radical as the square root of 8. Because square root of 8 is really, we're saying 4 times 2. Square root of 4 is 2. Can't reduce the square root of 2. It's going to be 2 square roots of 2. That would be in simplest form. If we can reduce it, if there's a perfect nth root, something that can be reduced out, we have to reduce it out. No radicands can contain fractions. I can't leave it as the square root of 1/3 or as a radical with a fraction inside. We've got to simplify it out. Interestingly enough, this is actually going to become the square root of 3 over 3. We need to have it in simplest form. And lastly, no radicals can appear in the denominator of a fraction. We can't leave it as 1 over the square root of 3. This just doesn't work. Interestingly enough, it would also be square root of 3. So we need all three of these rules to be true. We cannot have one of these. If one of them shows up, we've got to simplify it. We've got to reduce it. We have to break it down. Questions on this so far? So, you need these three. We're following these three rules. Now, there's other two properties of radicals. Product property says if I have two things multiplied together inside of a radical, I can break it up into two radicals with the same index. Or if I have two radicals with the same index being multiplied together, I can merge them into one radical with what's inside being multiplied. So we can pull them apart, put them back together, as long as the indexes are the same. Same with quotient property. If I have a fraction inside of a radical, we can split it up into two separate radicals. Or we can merge it back into one and simplify there. The only reason we would go from two radicals being divided to a radical with a fraction inside is if that fraction will reduce to an integer. We won't have a radical or a fraction anymore. But let's look at some examples here. First one we have is the cubed root of 12 times the cubed root of 18. There's not a number multiplied by itself 3 times. That gives us 12. And the same is true for 18. So what we can do is actually look at the factor trees of 12 and 18 and see how they reduce and if we can reduce them together. And I always start with the smallest prime number with my factor tree, so 2. Because 12 is going to be 2 times 6. 2 is prime, so we can look at 6, which is 2 times 3. Telling me that the prime factorization for 12 is 2 squared times 3. We can do the same thing with 18. 18 would be 2 times 9. And 9 is 3 times 3. Telling me its prime factorization is 2 times 3 squared. For me to be able to take a cubed root, I need groups of 3 of a factor. And as we can see here, cubed root of 12 is the cubed root of 2 squared times 3. Cubed root of 18 is 2 times 3 squared. There's not enough factors in either one on its own to be able to take a cubed root of it. Questions on any of this so far? Product property says that if I have two radicals with the same index being multiplied together, we can multiply what's inside. So that's telling me that I actually have the cubed root of 2 squared times 3 times 2 times 3 squared. We can multiply what's inside of them together. Two squared times 2 would be 2 cubed. We now have 3 2's. And our 3 times 3 squared would be 3 cubed. Now there's different ways we can go from here. One way is that we just say, because just like we put them together, we can break them back apart. I can say that this is the cubed root. Let's make that a little bit bigger. The cubed root of 2 cubed times the cubed root of 3 cubed. We just split it back apart. Cubed root of 2 cubed is 2. Cubed root of 3 cubed is 3. 2 times 3 is. So the cubed root of 12 times the cubed root of 18 is 6. Questions on this here? Now, another way we could have approached this, it doesn't change the answer. Take it, try. According to our property yesterday, since the 2 and 3 both have the same power, I can factor it out, yes? Which is telling me that I have 2 times 3 to the third. Well, those would cancel, telling me I have 2 times 3, which is still 6. Different ways we can get there, yes? Cubed root of 12. Because it's simplified nicely. Calculator will handle it just fine. Possibly, yeah. Yes. 4th root of 80 divided by the 4th root of 5. So we want to simplify these radicals as far as possible. And especially if they have perfect nth roots, we need them there. But also, we cannot have a radical in the bottom of the fraction. Different ways we can approach it. We can prime factorization 5 and 80 at the moment and go from there. But before we do that, is 80 divisible by 5? Yeah. So one thing we can do with this is just say this is the same as the 4th root of 80 divided by 5. So our number 3, for simplifying, not having a radical in the bottom of the fraction, we now do not have one in the bottom of the fraction, but we now have a radical inside, or a fraction inside that radical. So it's a different issue. But 80 divided by 5 is what? So we got rid of the radical out of the bottom of the fraction. We don't have a fraction inside the radical anymore because they divide nicely. So that's kind of the only reason we put them together. If they don't divide nicely, there's no reason to put it in fractional form inside the radical. Does that make sense? Because otherwise we'd have to break it right back apart and go through figuring out how to get that denominator simplified out. But now we're needing to find the 4th root of 16, which would be 2. If we're not sure about that, we can do the factor tree with it. The 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. And we have 1, 2, 3, 4 2's. Telling us it is 2 to the 4th. Or essentially, we'll say that the 4th root of 16 is the 4th root of 2 to the 4th, which lo and behold is 2. And well, since it came out to a integer solution, that means we could have done what? Put it in the calculator. Might need to check and see if it's full. Questions on either one of these here? Cubed root of 4 times cubed root of 128. I have a feeling the first place we're going now. Cubed root of 4 times the cubed root of 128. That tells us it is 8. Okay. Let's see how we can actually get there if we didn't use a calculator. Now the cubed root of 4 is going to be 2 squared. We could do a factor tree with that, but I feel like at this point we've done the fact that 4 is 2 squared enough times. We don't necessarily need to see that one written out. Now 128. Well, that's 2 times 64. 64 is 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. Makes sense since we're using 2 in a 3-digit number. We've got 1, 2, 3, 4, 5, 6, 7. So 128 is 2 to the 7th. If we want to make sure that we have the right one, we can plug it in the calculator and see that 2 to the 7th is indeed 128, exactly what we wanted. So the cubed root of 4 times the cubed root of 28 is the same as the cubed root of 2 squared times the cubed root of 2 to the 7th. Yep. So the cubed root of 2 squared times cubed root of 2 to the 7th, we multiply what's inside. 2 squared times 2 to the 7th would be 2 to the 9th. We multiply like bases, we add those exponents. 2 plus 7 would give us 9. Now the question is, what is the cubed root of 2 to the 9th? How many groups of 3 2's can we take out of 2 to the 9th? Now, if that's not as intuitive or if we're able to see it, let's go back to what we had before. The nth root of a to the x is equal to what? A to the x over n, yes? So a in our case for this is 2. As we look at the fractional exponent, the x, which goes on top, would be 9 in our case. N is 3. So the cubed root of 2 to the 9th is equal to 2 to the 9/3. What is 9/3? 3, yes? And 2 to the 3rd is 8, just like we got. So it is a little bit longer process and we have to do it by hand, but we do get to the same thing, same exact result. We ready for the last one of this type? Fifth root of 192 over the fifth root of 6. So we know what we're supposed to get. Now the first thing I would do here is, because we notice, or should notice, that 192 is divisible by 6. Now there's two ways that we can understand or know that those two are divisible. One, for a number to be divisible by 6, it also has to be divisible by both 2 and 3. 192 is definitely divisible by 2 because it's an even number. Divisibility of 3, if we add those digits together and that sum is divisible by 3, then the original number is also. So 1 plus 9 is 10, plus 2 is 12. 12 is indeed divisible by 3. So we know 192 is divisible by 3. The other method is I grab a calculator and say 192 divided by 6 is 32. Telling me I'm looking at the fifth root of 32, which is 2. Questions on this here? Questions on anything we've done so far? We ready for the next one? Well, as we've seen up to this point, cube root of 135, might as well just type in cube root of 135 and get our answer, yes? It gave us an irrational number, yes? So let's see what it says. Write each expression in simplest form. It does not say approximate, it does not say round, so we cannot take the decimal approximation. So we are going to have to factor tree, because we need the prime factorization, because we need to see what is going to simplify out of the radical and what's going to be left behind. So what's one of our prime numbers or prime factors of 135? Three. Because we can figure out what times 3 gives us 135. We can just go 135 divided by 3, which is 45. Interestingly enough, 3 is also a factor of 45. It'd be 3 and 15. And 15 is 3 and 5. Telling us that the prime factorization for 135 is 3 cubed times 5. So we can go on and replace 135 with 3 cubed times 5. Now at this point here, we could say that the cubed root of 3 to the third is 3. We can't take the cubed root of 5, simplify it there. Or we can use our product property. And I can split it up into each term. I can split it up with our cubed root of 3 to the third times the cubed root of 5. Now the cubed root of 3 to the third would be 3 times the cubed root of 5, because I only have one factor of 5, it's not going to simplify with that cubed root. I would need 2 more of them. Telling us that the cubed root of 135 is 3 cubed roots of 5. So really all of this is based off of those factor trees, being able to factor, simplify, and reduce. Questions on the cubed root of 135? So based off that one, we have probably a good chance that the fifth root of 7 over the fifth root of 8 is not going to reduce, and the calculator is just going to give us a decimal number. We're also probably not going to want to divide 7 by 8, because 7 and 8 do not divide nicely. So our big issue is the fact that we have that radical in the bottom of the fraction. Now the tempting thing is seeing how many 8s I need to get that fifth root to go away, yes? Well, I would need 4 more of them, because if I have the fifth root of 8 to the fifth power, those would simplify, those would reduce, yes? Before we do that, let's look at 8's factors, because 8's not prime. 8 would be what? 2 and 4 is 2 and 2. So 2 to the third is indeed 8. So we could have multiplied it by 8 4 times and got 8 to the fifth on bottom, but that also means I would actually be multiplying 2 to the, see here, 12th, which would simplify 2 times over. So really what we have is the fifth root of 7 over the fifth root of 2 to the third. Because this makes it nicer and a little bit simpler in a way to reduce. Because instead of looking at 8's, which would have gotten us way too many, and we'd had to simplify the numerator also at that point, we are now looking at it in factored form, simplified form. How many 2's do we need to simplify with that fifth root? Well, we would need 5 of them total, yes? How many do we currently have? We currently have 3, yes? So how many are we missing? 2. So what we can do is multiply the bottom of this by the fifth root of 2 squared. Because the fifth root of 2 cubed times the fifth root of 2 squared would get us the fifth root of 2 to the fifth. Because when we multiply like radicals, we multiply what's inside. And when we multiply like bases, we add those exponents. So 3 plus 2 gives us 5. But if I do it to the bottom of this fraction, I also have to do it to the top, because this is not an equation, it's an expression, so we have to have it have the same value. On top, 7 and 2 are not like bases, so we can't add the exponents. It's just going to be 7 times 2 squared. On bottom, the fifth root of 2 to the fifth is indeed 2. Do 7 and 2 squared have any common factors? Well, no, because 7's prime. It's not going to share any factors with it. We do need to check and make sure, because if the number 7, if it had actually been a number with 3 factors of 2, those 2 factors of 2 we add to it would simplify out. But that also means it would have had factors with 8 to begin with. And instead of leaving it as the fifth root of 7 times 2 squared, well, 7 times 2 squared is 28. We're just going to rewrite it as the fifth root of 28 over 2. 28 and 2 will not simplify because we don't actually have 28 on top. We have the fifth root of 28, which does not, well, it can divide by 2. We're just not going to do that. Questions on these here? Questions on this so far? Now, if that denominator had been a prime number, we don't have to do the factor tree. We can just multiply it by itself the number of times we need to simplify that radical. Cube root of 500. Well, just like the last so many, there's a good chance that is not going to, the calculator is not going to give us a nice answer. It's going to give us an irrational number. Well, we can start with 2 or we can start with 5. I'm going to start with 5 because 5 times 100 is 500. Incidentally, 5 times 20 is 100. And 5 times 4 is 20. and 4 is 2 times 2. So the prime factored form, the prime factorization of 500 is 2 squared times 3, 5 cubed, not 3. 2 squared times 5 cubed. We can break it up into its two forms. We have the cubed root of 2 squared times the cubed root of 5 cubed. Can we take the cubed root of 2 squared? No, we only have 2 2's. We need minimum 3. So that doesn't reduce. So we can include it as part of our answer, but since it didn't reduce, might as well just reset it back to 4. Cubed root of 4. Cubed root of 5 to the third would be 5. Telling us that we have 5 cubed roots of 4. If we had an extra 5, if it told us we're taking the cubed root of 5 to the fourth, we'd bring one out, we'd have one left over. Really telling us that we have 5 cubed roots of 20. 4 times 5 is 20. We'd multiply what we have left over back together. And that's it. Questions on this here? Questions on anything so far? 4 through to 19, or the 4 through to 4. We'll do that here in a second, but also the other question is sometimes did we get the right number? Because that's sometimes we're trying to figure out, did I factor it right? Did I do it right? Well, 5 times the cubed root of 4. This was our answer that we got. I can compare it to the cubed root of 500. They have the exact same decimal approximation, which means they are equivalent statements. So we have the right answer. It's a nice way to check. Are you ready for the last one of this type, or similar type? 4 through to 19 over the 4 through to 4. 4 through to 19 we can't take for sure. 19's prime. 4 is not prime. It's a composite number at this point. We could do the factor tree, but I think we know that 4 is 2 squared. Questions on this so far? There is something interesting about the 4th root of 2 squared. That index and the exponent are both even numbers and actually divisible, yes? So you don't have to write this down, but if we change that into a rational exponent, we'd have 2 or 4, or 2 to the 2/4, yes? 2/4 is what? So what that's telling me is that the square root of 2 and the 4th root of 4 should have the exact same value, and they do. However, it does not help us here. Because if we did this, that would mean I multiplied on top and bottom by the square root of 2. I can only multiply like radicals, so the indexes would have to be the same, which means we'd have to change it back from a square root to a 4th root for us to be able to multiply it with the 19. And we don't necessarily like having the 4th root of 19 times the square root of 2, two different radicals being multiplied together, especially if it doesn't actually prove anything useful. So unfortunately, at this juncture, we got to leave it as the 4th root of 2 squared. Doesn't help us. But it does help us in a sense of figuring out what we need to multiply on top and bottom to get that radical on bottom to go away. Because currently we have 2 2's in that 4th root. For it to simplify out, we need 4 of them. How many are we missing? 2. So we're going to multiply by the 4th root of 2 squared. Because on bottom, 2 squared times 2 squared would be 2 to the 4th, telling us that on bottom we have the 4th root of 2 to the 4th. And on top, we'd have the 4th root of 19 times 2 squared. Now the 4th root of 2 to the 4th is 2. On top, in that numerator, our 19 and 2 squared is not going to simplify. 19's prime. 2 squared does not have enough 2's. So 19 times 2 squared is 76. Showing us that the 4th root of 76 over 2 is our simplified form. Questions on this here? Questions on anything so far? We're ready for the last bit. Simplifying these complex or these irrational fractions. Again, you cannot have a square root in the bottom of the fraction. So, just like the previous problem, we need to multiply this by something, this fraction by something, to get that radical to go away. I'm just going to change the sign in the middle and see what happens. So if we multiply these together, 5 times 5 gives us 25. 5 times negative square root of 3 would be negative 5 square roots of 3. Square root of 3 times positive 5 would be plus 5 square roots of 3. And lastly, square root of 3 times negative square root of 3, we'd have negative, and our 3 times 3 would give us square root of 9. We'll deal with the numerator here in a second. But if we look at what we have, we do still have 25. Negative 5 square root of 3 plus 5 square root of 3 would be what? Negative 5 plus 5. 0. Minus, well, the square root of 9 is 3. So by changing the sign between our two terms from 5 plus the square root of 3 to 5 minus the square root of 3, and we multiply those together, we actually got an expression, or the denominator now has no radical in it. We were able to get it in a form where the radical on bottom is gone. But unfortunately, I can't just multiply the denominator by 5 minus the square root of 3. We also have to do it to the numerator. Well, 1 times 5 is 5. 1 times negative square root of 3 is negative square root of 3. Well, 5 minus the square root of 3, they aren't like terms. There's nothing we can reduce there, so it's just going to stay 5 minus the square root of 3 over 22, or negative square root of 3 plus 5 over 22. Same answer. Questions on how we did this here? Questions on anything we've done so far? And we know for certain that the 30xs would not take 1 over 5 plus the square root of 3 and give us a nice answer, because that's how these calculators work, right? Oh, wait, it actually did. That is the same answer. Negative square root of 3 plus 5 is 5 minus square root of 3. Either way. Questions on this here? 1 over 7, square root of 7 minus 2. Square root of 7 plus 2 over 3. Because we would be multiplying by the square root of 7 plus 2. Square root of 7 plus 2. Square root of 7 times the square root of 7 would be the square root of 49, which is just 7. Square root of 7 times 2, positive 2, is going to be plus 2 square roots of 7. Negative 2 times the square root of 7 will be negative 2 square roots of 7. And negative 2 times 2 is going to be negative 4. And well, the square root of 7 plus 2 times 1 is going to be the square root of 7 plus 2. Seven minus 4 is 3. Same exact answer. Now, unfortunately, the graphing calculator will not do this because it does not leave it in simplest radical form, simplest square root form. It turns it into decimals every single time. Questions on this here? Well, 4 over square root of 2 minus 5 square root of 3. Yep. As long as those numbers don't get way too big, that 30xf will do it every single time.